In this example, we're going to consider a somewhat more challenging programming problem related to finding percolation clusters. So, a percolation cluster is a cluster of connected sites on a lattice in which every site is either filled or empty. So, if we have a square lattice of sites like so, and these sites are filled like this, and the rest are empty, let's say, then these sites are connected and these sites are connected. The connections in my definition here are they need to be across near neighbor bonds, that is from here to here but not from here to there. And these sites are connected, and these ones are just empty, so they're not connected at all. So the problem that we're going to address here is an algorithm for finding all of the percolation clusters, that is, all of these connected clusters of sites on the lattice. And so here is a way of doing that, which is a little bit involved and so best described in words first. So we loop over all sites, and for every site we start an empty cluster. And then we put the site on a list to be checked. And I'm going to call that the TBC list. Okay, so while the TBC list is not empty, then we take the top item and ask if it's marked. When we visit it, it's going to be marked, as you'll see. I'm going to go through this whole thing and then kind of explain why we did it this way. So if the item is marked, is not marked, sorry, then so it needs to be both not marked, sorry, and filled. Okay, if it's both of those things, then we do the following. We mark it, we add it to the cluster, and we add its neighbors to the list to be checked. And after we've done that, we remove it from the list to be checked because we just got through checking it. When we're done with all that, when the TBC list is empty, then if the cluster we just built is not empty, then we save it and go on. So in the end we wind up with a list of clusters. So for example, we start with this site here. So we're going to loop over sites. We've got to scan through the sites in some order. We pick this site here. We start an empty cluster. We put the site on the list to be checked. Okay, while the list is not empty, well, this is the only one on it, we take the top item, that's this one, we ask if the item is not marked and filled. It's not marked, okay, we've just started looking at it, but it's not filled either. So we move on, and we remove it from the list to be checked. The cluster we built is not empty, so we don't save anything. We go on here, do the same thing. We get to this site here. Okay, that site is not marked and filled, so we mark it. And then we check its neighbors. We add its neighbors to the list to be checked. Well, okay, that's going to be these ones. And then when their turn comes, this one will be marked because it's filled, and its neighbor will be added to the list to be checked, and this one will be marked, and so forth. And those will all have been added to the cluster that we're building. And eventually we'll check all of the neighbors as we build out from this site. We'll check all of the neighbors. And they'll all fail eventually because this one's not filled and that one's not filled and that one's not filled and so forth. So they'll all fail. And so the cluster will stop and we save that cluster and then we go on maybe to this site and then we don't do anything and then we go to this site and it's filled and so its neighbors will be added to the list to be checked and it will be added to the cluster and marked, and so forth. So that algorithm allows us to explore outward every new cluster, and the point of the marking is to make sure that we don't keep visiting the same sites again. Because, for example, when we first encounter this site, we mark it, we add it to the cluster, we add this neighbor to the list to be checked, it comes along, it hasn't been marked, it gets marked, it's filled, and then we add its neighbors to the cluster. Well, that will add this one, we add its neighbors to the list to be checked, and that will add this one again to that list. And then we want to make sure that we don't just go on around forever, so when we come to that one, we discover it's been marked and we don't do anything else. So with an algorithm this complicated, it's important to really write it out in terms of what you would do if you were a very careful, very compulsive, very literal-minded person following the instructions. So you are the computer, as it were, and make sure that the instructions are so clear, that there'll be no ambiguity about what to do, and then think through very carefully, well, if I did exactly what this says, will it accomplish what I intended? In some way, a recipe for how you go about writing an algorithm for something slightly more complicated. So to begin with, we need some sort of a function for filling an array with random sites, under the assumption that that's what it is we want to look for percolation clusters in. So we need to know the fraction of sites that will be chosen to be 1. That'll be f, and we need to know the linear dimension n of the square array of sites that we're supposed to build. And so we want to say if random real is less than f, then we put a 1, otherwise we put a 0, so the random real will be less than f with probability f. So then you get a 1 with probability f, and you do that on an n by n table. So that will create a table that we can use to fill our array. Another useful thing, remember the part where we add the neighbors to the list to be checked. It'll be useful to be able to easily get a list of the neighbors of a given site, which we'll label by its ij coordinates. And that list naively would just be I plus 1 j, I minus 1 j, I j plus 1, and I j minus 1. But as we've discussed in previous example of the 2D Ising simulation, if we want to do this on periodic boundary conditions in order to avoid the problem of how to deal with these end conditions, if I were n, what do you mean by I plus 1? We're going to wrap around those shifted values a mod function with an offset of 1, and as I mentioned in the Ising example, that has the effect of mapping the value onto the range 1 to n. So it wraps around the edge of the array if you come to the edge. That is to say, the neighbor to the right of this site here, this neighbor right there, which isn't there, is actually this neighbor, as if an entire copy of the lattice were over here, and so this site would have a copy right there, and so the right-hand neighbor of this site is actually that one, and the left-hand neighbor of this site, there's a copy of the lattice over here, and so the left-hand neighbor of this site is this one, which is this site here. Okay, so so the neighbors function works like that. It's just the obvious thing, except wrapping these mods around in order to avoid falling off the edge of the array. So the real meat of the story, of course, is the function that calculates the clusters. And so it takes a frame as its input, and it would be useful to know what the dimension of the frame is. So we'll save that. And then we want to start out defining the function that tells whether things are marked, which will be called marked, and it will be a function of pairs, because that's how we're labeling our sites. We're going to start out defining that function to be false for all possible values. So that basically is unmarking all of the sites. Then we need this list that we're going to save the clusters on, because we're going to have more than one cluster, and that list will be called cluster list, so it gets to be set to be the empty list to begin with. And here's our big do loop in which we loop over all sites. So down at the bottom of this do loop, we're going to have looping over the indices of the sites, which we're going to call K and M. That'll be the X and Y indices, so to speak, of the sites that we're checking in turn. And so the guts of the do loop, well, we're supposed to start a new cluster every time we come to a new site, which is the cluster that that site may possibly generate. We're supposed to make a site list called to be checked, which originally gets set to be just having in it the site that we are now currently visiting. And then, while the to be checked list is not yet empty, we're supposed to take the top item off of the to be checked list. And it turns out we're going to need the I and J entries of that, which are just the two components of top. And then if that item is not marked, and it is also filled, which is to say that its IJ entry of frame is 1 instead of 0, okay, then we're supposed to do some things. We're supposed to mark it. So we change the definition of the function marked so that that site is now marked true. We append to the cluster list the site top, and we add to the be checked list the neighbors of top. And then we're done with the if statement. Those are the things we're supposed to do if the site that we peel off the top of the to be checked list is not marked and is full. And then whether or not we did anything, we're supposed to remove that site from the to be checked list. So we drop the top item from the to be checked list. And that's the end of the while loop. We keep doing that until the to be checked list is empty. Now, if the cluster that you formed in this way is itself not empty, then we're supposed to stick that cluster onto the cluster list. Otherwise, there's nothing to put on the cluster list, and so you don't do anything. And then you just go around and look at all the sites one after the other. And that's your do loop. And then when you're done, you report the cluster list, and that's the end. So it's a tricky little algorithm, but not hard to code. It basically codes exactly the way that the text that we wrote says. So that's the tricky part. Now we need something that draws the clusters so that we can see what we're doing. And that takes a list of clusters, which I'll call cluster list. And basically what I want to do is for each cluster, I want to make a list of, I want to draw the points where they go with a random color, just so the clusters will be different colors. So I'm going to finish typing this and then explain what I'm doing. Okay, so the idea is to make a table of graphical elements that then gets passed to graphics, and the table is one item in the table for every cluster in the cluster list. So the table is looping over the length of the cluster list, and you process each cluster in the cluster list, that is the ith cluster in the cluster list, separately. And what you do in processing it, first of all, is to make a list of disks out of what used to be a list of pairs, because the cluster list is a list of, ij pairs for the different sites in the cluster, and you give that disk a certain radius. And so this maps that function, turning the ij pairs in the cluster list into a disk. And then you stick on that a color, which you just choose randomly for every different cluster. So that draws the clusters. So to try this out, we'll set n equals 100. We'll, I don't have to call it frame, but I am going to. I'll fill the frame in this way. Then I will, maybe I'll call this, so as not to be confused with any other variable, my frame and my clusters. And then I want to draw them. Like that. Well, that didn't work out very nicely. Wonder what the problem is. I seem to have found a mistake, which is I need to append to the cluster list the cluster, not append. Append would generate an appended list, but not stick it back on cluster list. So let's see if that helps any. Well, that's better. Okay, so there you have all the different percolation clusters colored in random colors so that you can kind of tell where they are. So that's a fairly clever little piece of coding, but again, extremely short really, and very much following the idea of the algorithm as described on the page here. And that's again another example of the power of a relatively high-level language like Mathematica.